Hello everyone, welcome to the P1 program. This lecture is called P106, 107, right? So P107.1, that is what the lecture is called. In this lecture, we are going to discuss about the circular motion. So circular motion is the point of discussion here, right? So what happens when you move around, right? So when you move around in a circle, so you see that when you move around in a circle like this, you can see that when you complete one rotation, your initial position and final position will be the same, right? So delta of x or delta of position change will be equal to 0. So you can clearly see that there will be, so the average final velocity will be v average will be equal to 0. So also acceleration will be, average acceleration will be equal to 0. So this is a very unique basic representation. But when you are moving in circles and you have a constant velocity and all that, then that means something, right? So you're spending energy to do that. So maintaining that kind of a motion is very much complicated than these simple form. So let's look at ways to represent them, right? There are different aspects of circular motion, and let's see what happens. So if you have a circular motion, you can represent it in terms of the x and y axis, which is what we usually do, and we can represent a point in that moving body, a point in terms of a vector. And when it moves some distance, say delta, what, delta r, right? Delta r distance, when you move, the displacement is there, which is delta r, and then there is a circular path, which is the distance, right? So there is distance and displacement there. So what we can measure from this here is that okay, if you look at this motion, you can see that at every point in space the direction of motion is changing. So here it was the tangent, which is the direction of motion, is like this, and at this point it will be like this if it is moving in this direction. So the direction is actually changing fast, right? Every instant the direction is changing. So this is a complicated form of representation. So if you cannot just simply represent in terms of delta r by delta t, you cannot use that for some velocity equation, because the direction is actually changing rapidly. So it is very hard to keep track of the actual happening. So what we can do is that we can use some of the tools that we have studied in 103, right? So in lecture 103, I think, so in the 104 lectures we have looked at coordinate transformation. So let's use some of those aspects and get something beneficial for us. So let's do some physics with it. So if you have a circular path, which I have discussed here, okay, so if you have a circular path, an equation of a circle can be as simple as some x minus what, some x minus a the whole square plus y minus b the whole square can be equal to some r square, right? So this is a basic equation of a circle. So this circle will look like x minus a means the circle has a in x intercept a and y intercept b, and the circle has a radius r. So the center is around here, right? So it's around here and it has a radius of r. So it will look something like this, so with a radius r. So that's the equation of a circle, and that's how the circle looks like. So you can always look at each of the point in terms of x and y intercepts. You can look at it like that. Okay, you can use x and y intercepts to understand the location, and maybe you can find the velocity using these x and y coordinate axes, but that is very hard. So what we can do is that we can transform this kind of a form into a new form of a polar coordinate system. That is much more easier to understand, and we will get some additional information from that. So it's r theta new form, like x cap and y cap has become r cap and theta cap. So that's a new coordinate axis. And now if you remember, in 104.3 I have discussed about the rotational matrices. So rotational matrices I have discussed. Okay, so in rotational matrix, if you know what a rotational matrix, okay, I suggest you go back to 104.3 and refer the rotational matrix, how we derived rotational matrix and how we used it, and I'll do some symbol representation of that. So if you want, you can take a vector 3x cap plus 4y cap, right? So that's a vector in a two-dimensional space, and you can multiply the magnitude vectorially with the rotational matrix, which is cos theta times x cap and sine theta y cap, and then there is minus sine theta x cap and cos theta y cap, right? So you can vectorially multiply them both and you get something that is a in terms of a new coordinate axis system, which is the r and theta coordinate system, vector r and theta coordinate system. So that's the new coordinate transformation. Now when you multiply, what you get is that I'm going to substitute these values to be equal to 1, right? So I want unit vectors, that's why. Okay, so I just represented that, I just as an example for you guys to understand. Now I want unit vector, so I'm multiplying it with 1, and what you get is the new vector space, which is cos theta uh, cos theta times x. Okay, so that's cos theta what cos theta minus minus sine theta y cap, and this is x cap as one vector, one part of the 2 by 1 is to 2 vectors, one row and two columns. So x cap and sine theta uh, y cap plus cos theta uh, y cap. So this is also x cap, sorry about that. So that's the vector that you get when you multiply the row and column. So this row times what I did was that I multiplied with this row and this column first, and then this row again and this column second. So that's what I get, right? So this is the new vector and it has an x intercept and a y intercept. So what we can now write is down is that individual r and theta. So r will be at vector r cap of t, so it's a function of time. Theta is also a function of time, because if you rotate something, right, if you rotate something, then the angle will depend on time, so which position you are in, right, based upon some time r, right, the displacement in terms of some time, after some time when you go around like this, and the theta will increase with the time or decrease with time depending upon the point of origin that you choose, and or r will also increase or increase as well as decrease based upon the position you are in from the origin. So if that's the case, now what we can do is that now we can represent them the individual transformed matrices. R of t will be equal to some cos theta of t in the x cap axis plus sine theta. Okay, I'm taking these two things out, sine theta in the y cap axis, right, and theta of t, these are two unit vectors we got out of that. I just call them r and theta, and theta of t will be minus sine uh, theta of t in the x cap axis plus cos theta of t in the y cap axis. So that's the two vectors, right, unit vectors that we get, positional vectors. This is the new transformed coordinates, this is the transformed coordinates that we got. Okay, so now what we are going to do is that, okay, we are going to now we got the position in circular coordinates. So now what we are going to do is that to find the velocity, so to find out the velocity, what we can do is that it is constantly changing the direction, right? So velocity is constantly changing every moment velocity is changing. So velocity, the basic equation of velocity, if it is a unit vector uh, of velocity, then you can say that it will be d of unit vector r of t by dt. So, right, so now I can substitute that r of t back into this equation. From equation 1 we have r of t here, so I can substitute this r of t back into this equation. And now what I will get is that sum is equal to d by dt of some cos theta of t in the x cap direction plus sine theta of t in the y cap direction. So that's the r of t substituted back into this equation. Now I can do what I can do is that take the derivative and I get minus sine theta, and theta is also a function of time, so I have to take that derivative as well, right? So it's d theta of t by dt in the x cap direction plus cos theta, which is a derivative of sine theta from here, cos theta of t times d theta of t by dt, the chain rule, y cap, right? So that's radial vector now, v of r, right? So v of r will be the radial part of this vector. So we have two parts here, one part is r cap and the other part is theta cap. So we have to find both of these radial vectors velocities in the radial direction. So one is in the this direction. So if you have a circle like this, one direction, one will be in the direction of, okay, let's redraw. Okay, if you have a circle like this, then one velocity will be in the radial direction, that is this direction, the angular direction, that is this direction, which is theta cap, and the other one will be in the radial direction. So there is velocity in terms of two axes as xy, similar to that there is r and theta. So there is change in velocity in the r direction and theta direction as well. So we have to find them both, right? So I got that sine theta. So v of r, v in the radial direction is equal to sine theta minus sine theta. So I can take out the d theta by dt outside, and what I get inside is minus sine theta sine theta x cap plus cos theta of t y cap, right? So sine minus sine theta x cap plus cos theta y cap is this, right? Minus sine theta this, so it's theta cap. Okay, so it's theta cap, so that means velocity in the radial axis is equal to d theta by dt times theta cap of t, right? So theta cap of t, this is very important now. Okay, and now let's find out the velocity in terms of v theta, v in the theta cap direction. The theta cap direction, what is the velocity? What is the velocity of the unit vector? So that is d of theta by dt, right? So that's, as earlier it was d of r by dt in the radial direction, now in the theta cap direction. Let's find out that. So substitute the value from the equation 1 for theta, which is minus sine theta t, and I'm substituting that back into this equation, and I'll get, right, I'll get d by dt of minus sine sine theta in the x cap direction plus cos theta in the t in the y cap direction, right? That's what I get. And when I take the derivative of that, I get minus cos theta of t, and the chain rule again, d theta of t by dt in the x cap direction plus cos theta, that is minus sine theta of t, which is a function of t, times d theta by dt in the y cap direction, right? So that's what I'm going to get. I'm not going to write theta as anymore, theta as theta t anymore. Okay, I'm not going to write that, okay, because it's annoying, and it's, you have to remember that, okay, theta is a function of time, so r is a function of time, and everything else is a function of time. Okay, so from now onwards I'm going to write simply theta, right? So that's easier. Now we got that, so that's d theta, which is the velocity component in the theta cap direction. So that's velocity component in the theta cap direction. So that is equal to, I'm going to take out the d theta and outside. So I'm going to take out d theta outside and I get d theta by dt, right? The minus sign, took the minus sign out. Inside I get cos theta x cap plus sin theta y cap, right? So cos theta x cap plus sin theta y cap. So what's that, you have seen that. So cos theta x cap plus y sin theta y cap is r of t, right? So I'm going to substitute that back in here. So you get minus d theta by dt cos theta, which is r of t, r cap of t to be precise. So we got two equations. I'm going to write them down in a box. I'm going to write them both down in a box. So first one is v cap of r, which is the velocity in the r cap direction, which is the first coordinate axis, which is d theta by dt times theta cap, and the velocity in the theta direction, which is minus r cap direction d theta by dt, right? It was like that. Okay, I remember. I think it was right. Okay, it was right. Okay, so that's what we get. I'm going to call this equation 2. Okay, this is the velocity equation. Now let's find out this is the velocity component of individual axis, right? So v r means in the r direction. It means that if you are moving like this in the r cap direction, that is the radial direction, what is the velocity? In the angular direction like this, okay, what is the velocity? So that's v theta and v r. So you can see that x is connected, like x is connected to y, vr is connected to v theta, right? So velocity in the r direction is directly dependent upon the rate of change of theta, right? And also in the velocity in the theta cap direction is directly proportional to, so it's no, it's actually opposite. When it is, when d theta by dt is high, then in the theta cap the velocity will be smaller. So you can, this is non-intuitive, right? You cannot imagine this right out of the box. It's hard for most people to understand this without doing some mathematics. So that's the use of these two vectors right now. Now we got the velocity component. Let's find out the actual velocity. So we got the x component and y component of velocity, or r component or theta component is the same, two coordinate system. So we need to find out what the, if it was the position, then what the position based upon x and y. So if it was the position based on r and theta, or here we need to find out the velocity based on theta, r and theta, right? So velocity based on r and theta, what it is, so we need to find out that. So that is the velocity vector. So velocity vector, so let's find out velocity vector. Velocity vector v of t is equal to what, some dr, which is the radial location, right, displacement vector, by dt, right? So here r will be equal to some magnitude of r times the vector, right? So magnitude of times r times the vector, unit vector r. So r is a constant here, right? So this r is a constant, so you can easily write down that it is the r times the constant outside d r cap by dt, right? So r is a function of time. I'm not going to write that down anymore. So dr by dt, we have found out dr by dt, dr cap by dt, right? That's what we found out. What is dr cap by dt? So that is just dr cap by dt is just, okay, here. So dr cap by dt is this thing, right? So this thing, so that is d theta by dt times theta cap, right? So that is equal to magnitude of r times d theta by dt times theta cap, right? So that's the velocity vector in it for us. So velocity vector v is equal to in the, so that's the velocity vector. Now we have found out the component of velocity vector now. Okay, so what we can do now is that we have to simplify this. So velocity vector is equal to uh, some constant, which is the radius, times d theta by dt. So d theta by dt is called omega, which is called the angular velocity of a rotating body. So it's omega times theta cap. So velocity is just, so you can write a simple equation which is velocity is equal to r omega. So velocity is equal to r omega. So for a rotating body, velocity is equal to r omega. Okay. Now what was the position, right? We have found out the components of what each of the locations here, right? So we have found out the components of location, but what is the actual position? So if you want to look at the position in a circular motion, you can see that what happens with the axis, right? We have found out r theta and r theta, r cap and theta cap, right? So we have found out two coordinates. Now how can we represent that position? So if you look at a, a part of a circular path, right? This is the total displacement delta r if you want, and then there is the position will change from r1 theta 1 to uh, let's zoom out a bit, little bit. Okay, so the position is going to look like this. So it's r1 theta 1 to r2 theta 2. So the positional shift is going to be like that, and the velocity will be a tangent at each of these points, right? So velocity will also be a function of time. So if this is the angle theta, right? So this is the displacement that we had, which is delta r. Now this is the actual distance traveled, right? So that's the distance traveled. If you take this kind of a situation again, if you draw like this, and you can, what you can do is that you can draw a two what two triangles. Each of the whole angle is theta, so it's theta by 2, and this is going to be theta by 2 as well, right? So and this is the actual path taken by that body, and this is the displacement r. Okay, so that's the displacement, and this is called s arc length. Okay, so you can say that this component b, let x component be, so you can say directly from the equation using trigonometry, sine theta will be equal to sine theta by 2 will be equal to delta r, right? R by 2. So this is delta r here, so this is delta r here, delta r. So delta r by 2 change in position, which is this side. So this whole thing is delta r, right? Delta r. So the half of that will be delta r by 2, which is the opposite side, by hypotenuse, which is r, right? So that's the radius. Radius is the hypotenuse, so that is going to be equal to r. So that's going to be the sine theta by 2. So for the whole two triangles, it will be 2 sine theta. If you add them both together, 2 sine theta by 2, right? If you add them together, you get 2 times that. So it's 2 times delta r times r. The r can be multiplied, that from the denominator it can be multiplied, and 2 will cancel. So sine theta by 2 will be equal to, I just did that for fun. Okay, sine theta by 2 is equal to delta r times r, right? So that's the sign of the angle right there. So what is the displacement happen, right? How can we represent that displacement in terms of some value? So theta is going to be here theta is a actual value for particular value. So it can be a varying function, it can be varying, the theta can be anything, theta can be a function of time. Here r is going to be a constant if it is a unit circle, or if it is a circle with the radius r, so it's going to be a constant. So how can we make out something from that? So in order to solve this, I'm going to introduce some concept. Okay, a basic concept called small angle approximation, right? Small angle approximation. So before that, before going into small angle approximation, so I'm going to introduce something called the linear approximation. Okay, so most of you guys might have heard about it, but anyways, I'm going to explain, I have to explain everything, so I'm explaining this as well. So the small linear approximation states that f of x can be written as as x tends to a, f of x can be written as f of a plus some f dash of a, right, f dash of a times x minus a. Okay, this is called a linear approximation. So you have seen this in Taylor series with the additional powers plus f double dash of x a by x minus a, the x minus a the whole square by 2 and all that. You have seen that. Okay, you have seen it several times. So where does it come from? So this kind of a linear approximation. So for that, I'm going to define the df by df of x by dx, right? So that's differential or derivative of f with respect to x. So you can say that it must be equal to limit x tends to 0 f of x plus delta x, right, minus f of x, right? So by x plus delta x minus x, right? So that's df by dx. So you can see x and x will cancel, right, when you open the brackets, and you get you remained with that. So what you can do now, this is equal to f dash x, which is differential of x with f with respect to x. Now you can simplify that. You can simplify that for this limit, right? You can write down f, you can multiply this delta x to this side and you get f dash of x times, right, sorry about that, so f dash of x, what is happening, f dash of x times delta x must be must be equal to f of x plus delta x minus f of x. So you can write f of x must be equal to uh, f of x plus delta x minus f dash of x times delta x, right, times delta x. So that's linear approximation. That's the approximation that we do. For x tends to some a value, right, for x tends to some a value, f of x will be equal to f of x for x tends to some a will be equal to f of a minus f dash of a times delta x, right? So that will be that. So you can see that sine theta, if you have a function like sine theta, this is called linear approximation. Now I'm going to do use that linear approximation to something called small angle approximation. So sine theta will be sine at x tends to, or theta tends to 0, theta tends to 0, sine theta will be equal to sine 0, right, sine 0 minus f dash of a is just cos 0, right? So it's cos 0 times delta x, right? So that's delta x tends to 0 anyways. So delta x is delta theta, so delta theta tends to 0, it's almost small. So sine 0 is 0 minus cos 0 is 1 times 0 is 0, so it's approximately equal to 0. So sine 0 for small values, so what does this mean? So for small values, sine of a or x or something like that, where a is tends to some small values, it tends to 0, will be equal to a, right? So it will be equal to a. So that's the approximation that we are doing. So approximately equal to a or 0. If it is 0, then it's going to be 0. So that's called small angle approximation. So that's called small angle approximation, right? So that's something that we also need to use, right? If you look at the function itself, you can see that sine 5 degrees is around 0.8 or something like that, 0.08, sorry, 0.08. And also sine 10 is around approximately equal to 0.1. So it's almost small for sine value. Sine value will be equal to, if sine theta will be equal to theta, right? So sine theta will be equal to theta, so sine theta equal to is approximately equal to theta for small values of theta. Okay, so that's called small angle approximation. So if you want to use it, so now let's use that. Okay, if you have a triangle, two triangles like we had earlier, right? So we had earlier two triangles with each of this small angle theta and theta as well. If that's the case, then the arc length s and the displacement will be r, delta r if you want. So you can clearly see, if you take one triangle, so if the angle is much smaller, right, if it is a much smaller triangle, right, it is much smaller angle, theta is much smaller, theta is approximately equal to 0, then the arc length will be the same as that of what the arc length this will be almost closer to, for small and small values you can see arc length this will be much more closer to delta r, right? So it will be the same for small angles. So now you can do is that you can write down the using the sine theta. Sine of theta will be equal to some, let this be x and this be y, right? So this angle, this side be y, so it will be y by x in generic form. So y by x must be equal to some s by 2, right? So the this side is delta r, so it's delta r by 2 by r, right? So if you take the whole triangle, okay, if you take the whole triangle, you can see if this is the angle, this is the y, and this is the arc length, right, s, and this is the delta r, this is the r, and this is the theta, and this is x, right? So sine theta will be equal to some y by x, right? Some y by x, so it will be, it must be equal to s by, which is the r, delta r will be equal to s when it is smaller, so it will be sine theta will be equal to sine theta will be approximately equal to y by x must be approximately equal to s by r, right? So s is the arc length, which is s by r. So theta is equal to, using small angle approximation, sine theta will be approximately equal to theta. So that means that is approximately equal to s by r, and you can say that arc length s must be equal to some r theta, right? Approximately equal to some r theta. So that's arc length. So that's how you can find the arc length. This is also some additional information, anyways we need to use it right now. So if you have a circle like that and you have an angle like theta, right, this distance s can be represented as r times theta, right? So it's r times theta. If you have a full circle, right, if you have a full circle and you have to go around once, then that means the total distance traveled will be 2 pi r, right? So it's 2 pi r, that is the circumference, that must be equal to capital R, anyways. Okay, 2 pi r must be equal to r theta. That means theta here is equal to 2 pi. So theta is in terms of radians here. Theta is radians. So this is the radian kind angle value, the unit of theta. This is the radian unit of theta. So that's also useful. That's how you represent theta in terms of radians. So the half of the circle, right? The half of the circle will be uh, what, 2 pi by 2, right? So it's 2 pi by 2, that will be around pi. That's the total circumference, that's the total angle, that's the total angle here. And for the quarter of a circle, right, quarter of a circle, it will be 2 pi by 4, that will be pi by 2. So that's the angle, so that's 90 degrees. So pi by 2 is equal to 90 degree. So these are basic things I haven't mentioned, and I thought I need to mention. So you can say sine theta by cos theta is equal to tan theta. So if sine theta is equal to some, for theta going to 0, sine theta will be equal to theta, right? So it will be equal to approximately equal to theta. So you can see cos theta will be cos 0 is equal to 1, that means it will be equal to 1. So the tan theta must be equal to sine theta, tan theta must be approximately equal to sine theta, that is approximately equal to theta. So that's something, that is the small angle approximation that you can use when you have tan theta and sine theta with small angles. Now let's get back to our problem. Let's get back to our problem. So We have now we got delta r, which is the radial distance. Delta r is can be represented in terms of what, r times delta theta, right? So delta theta, we can represent that like that. Okay, we have mentioned that, right? If you have a circle like this, you can say that sine theta by 2, okay, this is theta, and this angle for this triangle, you can see sine theta by 2 is equal to delta r by r, right? So that's delta r by r. So sine theta must be equal to theta by 2 must be equal to um, theta by 2 must be equal to, or theta is equal to some r delta r by r. And so you can represent it in terms of delta theta. R can be represented in terms of delta, change in theta will be delta theta, right? So theta is now delta theta. So theta by 2, I just assumed it to be theta by 2. If you want, you can assume it to be theta. So it will be looking like this, something like this. So change in angle, right? So changing angle must be equal to the delta r must be equal to some approximation of r times delta theta. That's what we got out of that. Now what will be the velocity? So velocity is equal to d of delta r by dt, right? So that's velocity for you guys. Now what is going to be the velocity? So v is going to be equal to I'm going to take out the r because it's a constant, right? R is a constant, so I'm going to take out the r must be taken out, and you get d of um, I can substitute, I, I did substitute this, right? Delta r into this equation. I just substituted delta r into this equation, right? Into this equation, and you get, and I took out r outside, and you what is inside will be d times delta theta, right? So d times delta theta by, so what is happening, okay, sorry about that. So d times delta theta will be d by dt of what, delta theta, right? So that will be equal to r times omega, so omega v. So that's the velocity, angular velocity, omega v. So d theta by dt is equal to omega, we have mentioned that earlier, so that's why I substituted that in here. So velocity has now become, velocity is equal to r times d theta by dt in the theta cap direction, right? So that's the velocity in the theta cap direction. So if you look back at equation 3, right? So equation 3, you can remember that v is equal to r times, if you look back at the equation 2 here. So equation 2, we can see that r is equal, v is equal to r times d theta by dt in the theta cap direction. So if you look back at this equation, you can clearly see that's the same equation here, right? So the next thing that we are going to do is that, so that's the velocity for you guys. Now what I'm going to calculate is the final thing, one final thing. I know this is a long lecture, anyways. Acceleration is the next thing. So acceleration must be equal to some dv of t by dt, right? So you can substitute that the velocity equation in here, and you get d by dt of r times d theta of t by dt times theta cap, right? So theta cap of t. So that's the velocity equation substituted back in here, right? So that will be the acceleration. So acceleration is equal to, r is a constant, that's why it's taken outside, it can be taken outside. So acceleration is equal to r times d theta by dt of, okay, now I have to do this carefully. The first function, there are two functions here. So the first function is d theta by dt, this is the first function, right? This is the, okay, let's use another color. This is the first function, and this is the second function. So theta is also, theta cap is also a function of time, and theta is a function of time, right? So d theta by dt will be equal to, must be equal to the first function, derivative of the first function, which is d theta by dt. I just left it there. And now the derivative of the second function, which is d theta cap by dt, right, plus the derivative of the first function, which is equal to d square theta by dt square, right, times the second function, which is equal to theta cap of t, right. So that's what you get when you calculate the acceleration, right? Now let's simplify, let's do the actual thing, right? So a of t must be equal to, some r times, right, r times, let's do it correctly now. So these let's write this first, that's easier, right? So it's d square theta by dt square times theta cap of t, right, plus the second term, this is this term, right, this term, you have d theta by dt, right, times d theta cap by dt, right. So this d theta cap by dt can be d by dt of theta cap, right. Let's substitute theta cap back in this equation. So from equation 1 you can remember, from equation 1 you can see that where is equation 1? So from equation 1, so theta cap is equal to some sine theta minus sine theta and plus cos theta times y cap, right. So I'm going to substitute that back into this equation here. So it was minus sine theta, right. Okay, minus sine theta, right, sine theta, okay, sine theta in the x cap direction, right, plus cos theta in the y cap direction. So that's the whole thing, that's the whole thing, right. I have expanded that. Now let's simplify it into simple form, right. So a of t must be equal to, right, a of t must be equal to, let's use some different color. A of t must be equal to d square d square d square theta by dt square in the theta cap of t, the first thing itself, plus d theta by dt, d theta by dt times d by dt of minus sine theta is just minus cos theta times derivative of theta, which is d theta by dt in the x cap direction, right, and plus cos theta, the derivative of cos theta is just minus sine theta. So it's minus sine theta, right, sine theta times d theta by dt, which is the chain rule again, theta is also a function of time, times y cap in the y cap direction, right, the whole multiplied with an r, there is an r outside, so it's an r. So that's what you get. Now let's simplify that. You get a of t must be equal to r is outside, so r is taken outside, and inside we have d theta cap, right. So we have d theta cap, I hope you guys can see this. So we have inside, what we have is d square by dt square, right, and again d theta by dt inside again. So what you can do now, I can take the minus sign outside as well, right. So it's minus sign outside, and inside what we have is d theta square, also d theta, this is d theta by dt and this is also d theta by dt, it can be taken outside. So it's d theta by dt the whole square, right. So the whole square, um, the whole square, and what is inside is just cos theta, right, cos theta x cap plus sine theta y cap, right. So that's what inside is, right. That's what inside is, plus this term as well, right. So this term as well, so it's, so this term plus plus d square theta by dt square in the theta cap of t, theta cap of t. So that's what inside, that's what remaining, and r is a multiplied to both of them, right? So r is multiplied to both of them. Now if you look at this closely, this will be equal to, I think you guys won't be able to see anything because we are zoomed out so far. So you can see a of t, okay, a of t is equal to, look back, so okay, it's so big. A of t is equal to r times d theta square by dt, and this is equal to, this is cos theta x cap plus sin theta y cap is just theta cap, right? So this is just theta cap. So it's, you get r times, no sorry, this was r cap, right? This was r cap, it's not theta cap, so r cap. So what you get is just that, okay, what you get out of this is that r times d square theta by dt square in the theta cap, which is the second term, plus r times this d theta by dt the whole square, right? With a minus sign, I think, yes, with the minus sign, the minus sign in the r cap direction, right? So that's what you get. So that's the acceleration with respect to time, right? So that's the acceleration equation. So from equation 1, from equation 1 you can see that, so okay, from equation 1 we have substituted the r cap, okay. So now what we can do is that we can now write down the components of a theta, right? So a theta is the first component, which is r times d square theta by dt square, right? That's the first component, right? So that's the theta component, and then there is the r component of the acceleration, which is minus r times d theta by dt the whole square, right? So that's the second component, which is the r component of acceleration. So we have found out the both the components. So we can clearly see that a theta is equal to, theta component is equal to r times d square theta by dt square is called angular acceleration, which is r alpha, right? So it's angular acceleration alpha, and ar is equal to minus r times omega, right? D theta by dt is called omega, so it's omega square. So alpha is angular acceleration, and omega is angular frequency, right? Sorry, angular velocity. So angular velocity, okay. So angular frequency and angular acceleration has the same symbol, omega. They are both different, entirely different things, but they have the same symbol. So this is called angular velocity, right? Here it is called angular velocity. So with this long lecture, I think it's time to end this lecture, and we will do a problem in the next lecture. Okay, all the best for you guys.